All right. So I hope you guys see my screen now. So this week, the lab was about was an introduction to machine learning and particular focus on pipelines. And why that is important is because in general, when you are dealing with machine learning, you have a lot of moving pieces. So the example that I have here is for supervised learning, where you collect some data, you do some processing to your data. Either you fill in, deal with data that is missing, or you have null values. You do something called feature extraction, which means that you do some computation based on that raw data. You might want to do some sampling of your data if your data is too large, but with things like Spark, you could in principle process the full data set if you would have the resources available. Then you would split your data set into two, training and testing, or sometimes you could split it even into three data sets. But with your trained data set, the idea is that you will build a model that will learn from that data and then will generalize. And then so therefore, even once you have the training data, you still have to do a lot of other processing, right? Do some data pre-processing, learn some sort of algorithm, do hyperparameter tuning, which is the parameters particular of the algorithm. So you are in principle finding the best parameters for whatever algorithm you might be training. So in today's lab, there was the linear regression. So there was the penalty coefficient, coefficient, or the penalty value for the linear regression. And then in the case of the decision trees, you could think of the number of bins that you use to convert or to split a variable, but also you can start thinking of the size of the leaf of the tree, the size, the depth of the tree, and certainly many parameters that you could tune, trying to find the best one for your model. And then after that, you will perform some classification metrics or regression metrics, depending on the problem you're trying to solve. And then you will go back and test that model works well in your data set, in your test data set. So as you see, there are a lot of moving pieces. So it's important to have an infrastructure and that would allow you to have all those moving pieces working well together. And that is what pipelines would give you. So you could have, in this case, we had, for the lab, there were only 2 stages, but you can think of each one of these little steps being one of those stages. And that certainly will increase the number of moving pieces. All right. Before we start, any questions related to this week lab or any other question in general? I know some people were asking that we go into some more details in some cases. So I ask you please to take the opportunity to ask questions if you feel that you want to explore something further. This is your chance to do so. All right. So the lab included data coming from the machine learning repository, and it had 4 variables and a predicted variable. So this is the typical setup that you would have for a regression. So I assume that everybody read what the setup of the problem is, which is very important in general to understand what is that you're trying to solve before just launching or throwing algorithms at the data. It's good to have a good understanding of your problem, and that's what that business understanding the first part is. The next few sections, in a way, are repetition of what you guys are familiar. So I'm going to go a little bit faster in the first few sessions so we can cover the full notebook. Unless somebody has some question, I'm going to quickly go over them. So the first one is just to look at the location of your data. So in this case, a file path within Databricks. So in here we see that the files are in this particular location, and they're tab separated values. So if we were to take a sample of that data set with the command head, we can see that that is the case, that there are four columns, and then that the last column is the one that we were trying to predict. So actually 5 columns in total. With so the first 4 columns would be your X matrix, and the last column would be your Y matrix, or your target variable. We see some of this before, so I'm going to go by. So how would you read it? Well, you could read it as an RDD, and you guys are already very familiar with this. So you will be reading this particular text file, and then you would pass the full path. Now, notice that we could, in principle, also pass one of the files, but since we're passing the folder, the full folder, we are in principle reading all the files within that folder. And if we take the first 5 rows, this is what we would get. So this is the /tab /t, which means that that is a tab character, and that's simply how this particular file was stored. So we could, in principle, use, we could read it in many different ways. So there is the reader for, if we want to read actually as a data frame, we can then pass the following pass, the format, in this case CSV, and several options. So we're saying that this particular file has a header to infer the schema, meaning finding what are the types of each one of those columns. We're passing the delimiter, so in this case tabs, and the path. So actually let's do that.
Armando, there was a question about, can you use a mixture of file formats in the directory? And the answer is, if you're reading the directory as your source, like we did here, yeah, all the files need to be in the same format, and they will all be concatenated and loaded at once. Yeah. If you want to use different formats, you just need to specify the individual file names. Mm-hmm. And they will be loaded individually into different data frames.
Yeah, I agree. Yeah, that is not practical. Certainly, if you put them all in the same folder, the expectation, I would say, is that they're all in the same format. Yeah, thank you for answering. All right. So we can see the different types, since we're asking Spark to infer the types, and in this case, all of them are double. So that is good. But there are times where that might fail, or you might want to give or explicitly specify the type, the data type of whatever you're reading.
Armando, just a quick note here to people who are going to use something like Vanilla Spark. Vanilla Spark will, when you read a CSV, will identify everything as a string. This is the specific Databricks connector that seems to be working a bit better, but if you just read a CSV file using vanilla Spark, not through Databricks, it will not be able to infer the formats as here, and then you'll actually need to provide a schema for it.
Yes. Right. So if we were to look at this particular data frame, we see that there are the 4 columns that we specify, and then our target. All right. But as it was mentioned before, we can actually specify the type of each one of the columns explicitly, and you do that by using struct type. And in the struct type, you would have to specify the struct field, where you would specify the name. So that is the first element of this function, and then the type, in this case, double type, which we have imported from SQL types, PySpark SQL types. And then true, which means that that particular column can be nullable, meaning that there could be null values. So once we have specified that, let's make sure I run it. And what changes is that you notice here we don't have infer schema true, but we actually explicitly passing the schema, in this case, that custom schema that we built. So in principle, in this case, since we're doubles and it worked out well in the previous example, that might not be the case for whatever data you might have, and that's where you want to explicitly pass the data type.
Armando, there was a quick question there. Which one of the method is more efficient? And actually, the one where you provide the schema is more efficient, because Spark doesn't need to read the file to infer the schema for you.
Yeah.
So you will lose a bit of efficiency if you wanted to automatically infer the schema.
Right, exactly. Yeah. To infer the schema, you have to read the data and then define the type, while you right here, you're explicitly saying what the type is. So yes, absolutely. So you can access the types of each one of the columns by doing D types, and in this case, as we specified, they're all double. So all looks good here. You can explicitly, or this is particular to Databricks, you guys are already familiar with that. If we look at the content of the data frame, it should give exactly the same as we had before. Or it should be, yeah, it is looking after the same data. So they are in the process of machine learning that we were looking at the beginning. I think, well, here we had raw data collection. I think there was a box missing here, which is data exploration. And that includes understanding the quality of your data and making sure that whatever assumptions you might have of the model make sense. And then that's where business understanding would be useful for you. So all right, so let's sorry, just 1 second, please. If we sorry, yeah. Okay, sorry. So yeah, exploring the data is very important. So typically what you would do is somewhat what we did last session, where you were doing some histograms. Another very useful visualization tool for this sort of exploration is doing scatter plots, and that's what we are doing in this particular section. So we are would be doing scatter plots of each one of those two variables. And the idea here is to visualize the correlation between the variables. So ideally, when you build a model, you want to make sure that the model, the variables that you choose to build that model are highly correlated with the variable that you're trying to predict, and uncorrelated among them. And why is that useful is because, well, in principle, you could, if they're highly correlated, then you would be able to explain, or you would be able, you have to be careful with correlation and causation. But in this case, you would be able to find the relationship between the target variable and the input variable. And if you have many of variables that are correlated among themselves, the problem is that by adding each one of those, you're not gaining any power, because in a way you already are having the component for that one of those highly correlated variables would be pointing to in the same direction as the combination of all of them together. So here, in this case, for educational purposes, that's where we show that you can actually start using just regular SQL statements. And in this particular case, we register the data frame as a table, and then so we give the data frame, and we give a name for that table, so we can call it power plant. And because we might be running this several times, and just for sanity, for your own sanity, it will be a good idea to, if that table exists, you would drop it, and then you would actually delete the data associated with that data. Delete the data associated with that table. Sorry. And that's what we do here. In principle, the same sort of plots you can do using the regular display method on the data frame. But again, this is for educational purposes, and just to show you that you can directly put SQL code into one of the cells of the notebook. So in this particular case, we're doing a select star from power plant. So what this is just showing all the rows and all the columns of this particular table. And this, in a way, is equivalent to doing display of SQL context, SQL, and then the SQL statement, which in a way is equivalent to do a display of this power plant DF, which is exactly what we did in the previous here, right? That will give the exact same result. So let's just run it. And yeah, that looks good. And we can do other SQL commands. So in this case, describe. So we are describing each one of the columns of that table. So in this case, we're getting that the data of that, the type of that, or each one of those columns is double, which is what we would expect. So here are the definition of each one of the columns. So the atmospheric temperature, exhaust vacuum speed, atmospheric pressure, relative humidity, and then what the target variable is the power output. And more information for each one of those variables and the meaning of all that, make sure that you follow the links and read more about it. So we can do things like describe. So here, in a way, we're going back to the data frame. So this particular DF is just exactly, it should be contain the same data that we had previously in the data frame. But this is a way to show you that you can then, from a table, you can convert back to a data frame. And this is the way of doing it. And so once you have a data frame, you can do things like describe, which will give you some statistical summary for each one of the columns, of the numerical columns. So in this case, the count, the mean, standard deviation, and the minimum and maximum. All right, so that is good. Next, we will visualize the data. So I was saying before, sometimes it's good to start looking at things like not only the histograms, but also, I was just checking the name of the data frame, but also this two-dimensional, or this scatter plot, which in this case we are seeing that there is a high relation between power and temperature. So in this case, what we're trying to predict is the power, which is the last column. So this is telling us probably that if we use the temperature as input for our model, we could in principle have a good prediction of the power. You see this looks very much like a line. So then what this is saying is that as the temperature increases, the power decreases, given that the temperature is the input. I actually don't like this. I would rather swap the labels, but that's what the lab was requesting. Just because it's a bit confusing. I mean, people are used to having the x-axis on the x. But then you could do other things. So if we add cell above, and then we do display LDF. I think one that I like doing that would combine oh, it's not here. Which we saw last time, which was scatter. So it will be sort of like a grid, like scatter matrix is called. So on the diagonal would have a histogram for the variable, and then on the off diagonal would have the scatter plot for each one of the for each combination, or for each crossing of the variables. And I think that is not here. That's not one of the options, but that's something that is available. Matplotlib scatter matrix. Yeah, so something like this, where you would have scatter for each one of the variables. So in this case, there are 4 variables, and then in the middle you would have, in this case, the kernel density estimation, or you could have a histogram as well. Anyway, let's continue, and then similar for the other variables, scatter plot of each one of them versus power, and then similar here, pressure versus power. So again, this might look like as the pressure increases, the power increases. So that all looks good until there, and then similar for the humidity. Any questions until here? No questions. Okay. Then the part 5, the next session refers to preparing the data. So in this case, we are trying to build a model, and in the case of the predictor that we're trying to use, which is a linear regression, later we will use a decision tree, and later a random forest, would expect that the input would be vector. So let me just so in this case, So let's try to get an image here. So what we're trying to, this is our prediction, and we have X, which would be a matrix, and B would be the vector of the coefficients, and then we will have an intercept, which will be just another coefficient. So each one of the rows of this matrix X could be viewed as a vector itself. And that's what we do with vector assembler. We are assembling different columns into one vector. Right. So we are assembling, yes, several columns into one vector. So you would call you would call the vector assembler, and then you would set what are the input columns. In this case, the input columns are the first 4 columns of our data frame. So we'll pass them as a list, and then the output would be a new column into that data frame, and we call that column features. So I think it might be better to actually visualize or look at the output of that, and that might help. Let's see. Yeah. It's hard to, I don't know if we can draw here. Let me see. So let's see. Oh, this might not be good. Right. So let's say we have 4 columns, right? 1, 2, 3, 4. This is sort of me drawing with a mouse. It might not be the best. So what we're saying is take all these 4 columns and then convert them. You kind of do. Probably this was not a good idea for drawing. And then convert them into another column, and this one column would have will have all these 4 columns as vectors, right? So we're combining all of them. That could be confusing sometimes, but that is actually all that is doing. Okay. I think at some point we will run it. That might that might become a little bit more clear. Okay. The next thing in this pipeline would be to do split our data set. So we would leave some of the data randomly, assign it to the training set, and then we will assign another percentage to the testing set. So one typical way of splitting is 80-20, and that's what we pass to this random split. That is one of the methods of a data frame, and it would return 2 data frames, one that will contain the split for the first percentage, and then the second one, the split for the second percentage. And then since we are going to be using this too often, a good idea in this case will be to cache them. So let's run that. All good until here. The next thing would be to use or to build the linear regressor. So in this case, the linear regressor is within PySpark ML regression. And once you train the regressor, what you will get would be a linear regression model. So it would be a different type, right? But that one type is the one that you would use, say, to then evaluate evaluate the model or apply that model to new data, or find out what are the parameters of that particular model. And then the other important part is pipelines, which is just a way to stitching all those little pieces so that you have less chance of making mistakes. If, say, for instance, you invert the order or you forget to set a particular parameter, the pipeline would allow you to just not have to worry about it and stitching them all. Another way of accessing or understanding what the meaning of the parameters is by using the method explain params, and then you could see what the output of that is. So it would give you each one of the parameters that you can set for this particular regressor, for this particular linear regression. But if you, for whatever reason, you might not want to look at that, you can remember that you can always go back and look to the API, so you can see. And here in the API, this is the one for Scala, which I find somewhat easier to read and search. Here are the exact same parameters, and they would explain what each one of those parameters is. So then actually what we did was this one, explain params, explain all the parameters for this instance. All right, so actually we run that, and all good until here. Now that we have built or defined our linear regressor, we will set the parameters, some of which that we saw by calling explain parameters. In this case, the values are given to you, so you don't have to find them or figure a way to how to get those values. So they're already set for you. So then the label column in this case would be the target variable, and this is the last column of our data frame, which was PE. The maximum number of iteration, in this case, we set to 100, and the regularization parameter we set to 0.1. So I'm gonna just quickly look. Just look at the formula. So what that particular parameter is if you have a cost function that is that you're trying to minimize the error square, meaning that this y is your target variable, so in this case the PE column, and then your prediction, since we're dealing with linear regressions, would be a coefficient that's what you're trying to find, times each one of the columns that you have as inputs. So if you subtract the target minus the prediction, and then take that square, so you just have so the direction of the difference doesn't matter, just the size of it. And then you add a penalty term, and that is what this that 0.1 that was set for that particular regressor corresponds to this lambda parameter. Actually, this is for L1 penalty, and I think that one here is for elastic net. So actually, it is a little bit different. The regression is, the cost function will be slightly different, but the idea is somewhat similar, that you have a penalty function that would apply to the coefficients And the goal of the penalty function is to make sure that there are no weights that would, that maybe some of the weights will grow too much, and then that will in turn cause overfitting. So let me see if I can find, let's go, and yes, so I found one here. So that is actually the penalty function. And that parameter that we have is this alpha parameter. So if alpha is equal to 1, then we will do the penalty function would then turn into this sort of function, which is called the L1 penalty, because we are penalizing the magnitude of the coefficients. If alpha is 0, then we would have a ridge regression, which is a type of regression where the penalty is equal to the square of the coefficients. So is the sum of all the coefficients square. And then somewhere in between would be a combination of both sort of penalties. So that's what we do here by setting those different parameters. And then we build the pipeline. And the pipeline would have different stages. Each one of the stages would be a different processing unit of the data. So first we would apply that vectorizer. So remember that that's the one that would convert the columns into vectors. And then the next stage would be the regressor. So notice that this particular pipeline is very, very simple, only would have 2 stages. But if you have a more complex workflow, you might have multiple stages. So more than 2, certainly, it is very common in practice. And then after you have built that particular pipeline, you could actually just fit the pipeline, which what it would do is first transform the data using the vectorizer, and then find the optimization for the linear regressor using the settings that we put in here. So this should be fairly quick, and in fact it is. Any questions until here?
Hey, Amanda, I have a question.
Yes.
You said the regular parameter. You basically said the L1 penalty parameter?
No, this is elastic net optimization, which is this sort of penalty. So alpha is what we said as 0.1. So it's a combination between L1 and L2. This is L2, and this one here is L1. So it would be 0.1 L1 and 0.9 L2.
Okay, I see. Thank you.
So it's the type of regression here is the elastic net, which is a combination of both. All right. So certainly, I mean, I'm skipping over a lot of the details of the machine learning. I mean, the whole purpose here is to learn how to use Spark to do regression and machine learning in general. But if you have more questions, feel free to ask me more questions related to machine learning. I'll be happy to answer them. Now, how do you access then, after you have trained your model, how would you access the parameters? So remember that the pipeline had different stages. The first stage was the vectorizer. The second stage was the linear regressor. Therefore, the intercept, which is related to the regressor, would be in on the stage 1. So the indexing starts at 0. Stage 0 would be the vectorizer, and stage 1 will be the regressor. So that's how what we are saying here is from the linear model that we obtain after we perform the fit on the training data, we obtain this linear regression model. And the type of that linear regression model is the one that, here is this one, a linear regression model. And that particular model comes from a pipeline, and that pipeline would have stages. So again, the first stage would be the regressor. And then, so what we're saying here, from the regressor, get the intercept and assign it to this variable. From the regressor, get the coefficient and assign it to this variable weights. So in this case, because we had 4 input columns, we'll have 4 coefficients. And then here we're simply getting the names for those columns. So we are selecting from the columns in the data frame those columns that are not equal to the target variable. And then here, this is just a regular Python. We are zipping those 2 lists, with the one for the weights and the one for the names. And we would sort those by, so this is all regular Python, and we would sort those by the first element of the tuple, which is the weight, given more, or sorting the ones that have the higher weight first. And then this is just with the purpose that you can print the linear equation. So in this case, the linear equation would be the intercept plus each one of the coefficients, for each one of the columns. So again, this would look something like, something like this, right? We have some coefficients, and then we have the intercept. All right, so what do we do next? Well, we could actually go and see how well that particular model did on the testing set. So for evaluating that model, we would call transform, and we would pass the test data set to transform, and it would produce a data frame. And so from that data frame, we would select few columns. In this case, the 4 columns that are the input columns, the target variable, and the predicted target variable. So we run that, and we just do a simple visual inspection of the first few. That looks good. What other things can we do? Well, we can, if we can do something maybe like a scatter plot. It would be a good idea, right? And so the scatter plot that we would do, oh, look, there it is. Yeah, that looks good. That is the one that I was actually looking for before. So the scatter plot here is the one that would be interested is the predicted, which is this one here. Sorry, the target and the predicted. So we're looking for this particular scatter plot. So it seems like for the most part, the prediction looks pretty good comparable to the target. But of course, we would like to quantify that, and that's what we'll do next. If you notice, the lower part of this matrix is somewhat symmetric, or like a mirror version of the top part of the matrix. And then, so actually in here, we can see the same scatter plots that we did at the beginning when we were plotting the power versus each one of the inputs. So that is another way of doing it, just all in one shot. All right.
Armando?
Yes.
Can you just click on the plot option so people can see how to do that all at once?
Yeah, so I clicked in here, and then I selected scatter. And
yeah,
by default, it would set the values being each one of the columns, right? Yeah, each one of the inputs. But you could select. So in this case, we had PE, RH, AP, and V. Yeah. Let's say that we want to remove V for whatever reason. And let's say, yeah, just that. And then we do that. So we're able to only plot 3. Right. Yeah, but you can change more options here. All right. Good. So as I was saying, some visual inspection, both on the scatter and looking at directly at the data, tells that seems like this model is doing all right. But we would like to actually quantify it. And there are different ways of measuring or quantifying the goodness of a model. In this case, the linear regression, one of the most typical ones is the root mean square error. And the definition of it is explaining here, where you would have the predicted, in this case, and the target. You take the difference, square, and divide by the square root of n. So the goal here would be, if they're equal to each other, each one of the predictions is equal to the true value, then this RMSE will be equal to 0. So that will be the ideal model. So Spark already has all those evaluators for you. So what you would do in this case would be to just simply say which one is the column that you would use as the prediction column and which one is the label column. So our target column, in this case PE, and the prediction column is the one that we define being predicted PE. And the metric in this case is called RMSE, but there are other metrics as well that you could use. In fact, I think the next section we looked at the R-square, which is another metric that becomes useful when it comes to evaluating regressions. So in this case, very straightforward. You didn't have to do any calculations. You didn't have to implement the R-square. So I imagine it's optimized, so you don't have to worry about how those calculations are done. So yeah, all you have to do is when you have this regression evaluator, you would then evaluate that by passing a data frame. And from that data frame, we would use the 2 columns that you would set here as the prediction. Okay. So the other metric that could be used is R-square. So this is a metric that goes between 0 and 1. So the closer that metric is to 1, the better the model is. So this is what percentage of the variance is explained by our model. So all you would have to do is, instead of passing the metric name to be RMSE, like in the previous case, you pass the metric name to be R-square. I think somebody didn't. So sorry, I'm gonna mute everyone just because I think somebody forgot to, and it's making some noise. So if you need to talk, please unmute again. All right. So yes, this R2 matrix, R2 value returns 0.93. So yeah, this is telling us that this particular model seems to be an okay model. But then, of course, how good is your model would also depend on the context, the sort of data, and what sort of problem that you're trying to solve. So in here, again, this goes back to doing stuff in SQL, but you could do this directly with data frames. So remember that we, in the previous section, we used, in the previous lab week, we used with column. So we would pass with column equal, so let's say this residual error, and then you would pass the definition of that residual error. But here is in a way to showcase that you could do this also. If you only know SQL, you could in principle do the same operations in the data frame. So we are creating two new columns we're creating: the residual error column and the width RMSE column, which we define here. So the residual error is one minus the other, and the RMSE and the and the RMSE for the other column. So if we were to explore the values of that, I think I missed something here. I missed to run this one. Yeah. Okay. And then, so if we want to explore the RMSE values for this model, we could do so by just selecting that one column and making a histogram out of that. So to do that, you would select the type of plot here to be the histogram, and plot options, you can change the number of bins. So let's say, I don't know, just for fun, let's put it to 25, and then we'll get the histogram. So the idea here would be that we're expecting that within two RMSE, if this particular errors are distributed as a Gaussian distribution, as within one RMSE would have 68% of the data, and that's what we are doing in the next cell. Within two standard deviation would be somewhere close to 97%. So the calculation here, again, is to showcase just regular SQL, and how would you then, how can you integrate SQL into your workflow? So we were to run this and then select to do it as a pie chart. You could do so, but you could also say, for instance, do it as a histogram. Maybe not so useful. Yeah, so as a pie chart. The full area would be 100%, and within one RMSE would be the first one, which corresponds to 68%, and 1 and 2 will correspond to the 97%. So again, this is somewhat validating our model and telling us that the model that we built is statistically sound. Any questions until here? All right, let's go on then. The next step is to tune our model. So how would you tune your model is by doing something called cross-validation. And cross-validation, I think I have a slide. There you go. Yes, cross-validation is a process by which you would split your data set. In this particular diagram, the data set is split into 10 pieces. And you would train your model with, in this case, 9 of those 10 pieces. Sorry, 3, 5, 2, 4, 6, 8, 10, yeah. So you would train your model with 9 out of those 10 pieces, and then you would use the last piece to evaluate. And then that piece that you use to evaluate, you sort of choose each one of those 10, and then you would choose the best model by combining the metrics for each one of those test folds, so the one that you left out. In this particular example, we are using 3 folds, so meaning we're using 3 partitions. And in this case, the parameter that we're trying to tune is the regularization parameter. If you remember previously, we set that to 0.01. So that was just given to us, but most cases you would have to find what is the best parameter for your model, or best set of parameters. In this case, we just have one parameter, which is the penalty function. So again, very easy to build. So we would pass the cross validator, and you could pass actually for the cross validator to work. You would have to say what is that you're trying to estimate. So what is the model, or what would you use to build the model, and what would you use to evaluate the model. So remember that this regression evaluator is the one that we defined previously. And I think with the metric being the R2 metric. So what it's going to do is calculate, build the model using the regression pipeline, and evaluate using the evaluator, and splitting the data into three folds. So again, very easily you could then build that parameter grid. And you could have multiple grids. In this case, we just have one parameter, so very simple. We have to set which one is the parameter that we're trying to build. In this case, from the linear regression, the regularization parameter, and what are the values that we're gonna scan over. So actually, let me just parameter search grid. So just trying to see show another image here. So this particular image shows you what you're doing with this grid search. So you might have, in this case, is only two parameters. So you would give values for each one of the parameters. So in the X direction, or the first parameter and the second parameter. And for each one of those points, each one of those crossings of value for parameter 1, value for parameter 2, you would train a model. The same thing for each one of the dots. And you would train a model, and then you would evaluate the model with the fold that you left out from training the model. So this sort of equal space or evenly spaced parameter search can lead to trouble. In particular, let's say that your actually best point would be somewhere between those two points, those two parameter values that you set, and you might you might miss it. So one alternative is to, of course, give more granular search, or give more parameters. But remember that this is very computationally intensive, because for each one of those crossings, you're training a brand new model. So that could be very expensive. So one alternative could be to use a random parameter grid, where you would give random values in the x-axis and random values on the y-axis, or the second parameter. And you might be able to then get somewhere closer to that optimal point. Anyway, in this particular case, we're not using random search, but you could also use random search for building your grid. So that's what we do here. We are then passing, for the cross validator, we pass the parameter grid that is built here for us. And then finally, this will look very similar to the method that we used to train the pipeline. And it looks very much the same as if you just directly train a linear regression on top of the data set. So this would be very, very similar. So you would train this cross validator, so you would fit it into the data frame. And notice that here, what we're getting is the best model. So in this case here, the cross validator is here. That would require, as we saw, an estimator, an evaluator, and the number of folds. And it would return a cross-validator model, and from that model we are selecting the best model. So this best model would have the best parameters based on the evaluator that we have set up, that we had set up. Yes. So this in principle can take some time because you are running almost 200 jobs. And how is that? Well, we have the parameter space. In this case, we set 10 points, and then times 3 folds. So that would give, so it's more like 30. I don't know why they come up with 200. Because we're only optimizing into one parameter. So it's more like 30 jobs.
Yeah, no, but don't forget that you have the validation, the vectorizing steps, and all.
Oh yes, you're right. That's right. That's where yes. Although so the grid size is 10 times the folds is 3. But yes, you're right. All the other steps that we're missing. So that would add up. So yes, that's something to say that this can quickly go out of control if you have, let's say, 10 parameters to tune. It would quickly grow. It would grow exponentially. So so you might not want to try every single parameter in your grid search. All right. So right, so then notice that here I'm saying just give me the best model. So this best model, what I can do with that best model is then go and apply that best model to our testing data set. So very similar to what we did before. We apply that to the test data set and then select the output columns. In this case, the input or the X matrix, the target variable, and the predicted column. And how would we evaluate that? Well, we have the regression evaluator, and we would evaluate having or using the R2, the metric R2. And in this case, we get the same value for R2 and RMSE in both cases. And the reason for that is that, well, let's see what was the value, or what was the parameter that was used to optimize this particular model. Remember that we had a grid and we're trying to find the penalty. So we had that value set to 0.01. This is, I don't know if this changed now in Spark, that you can access the parameter in Python. But then in this case, there's this reaching through the GMV version of the API. So then this is sort of like the trick part. For those of you not familiar with Java, that's what this part is doing. So we are selecting the last stage, and the last stage, that is what this index, this negative indexing means in Python, is the first stage, which is the regression. And then from that, we are getting the regularization parameter. And this regularization parameter, the value is 0.01, which is the exact same value that we had set for the very first model that we built. So therefore, that's why the two models are equal to each other. All right. So the next section we do similar, but for the decision tree. So for decision trees are typically used for classification. So you would have two classes, so binary classification, and you would want to split them. But you can also use them for regression. And in this case, the setup would be very similar to what we saw before. We set, for this regressor, we set what is the prediction column, so what would be the output of that regressor. The features column, remember that this is the column that would have the vectors that we built with the vectorizer. and then the max bins. And the max bins is for each one of the variables, how many bins we would use. So how would we, in a way, convert that, or would discretize that variable? Yes, discretize that that column. So we're saying to use 100 bins to discretize that particular column. And similarly, we can build the pipeline. So this is the exact same thing that we did before, but in this case, the stages would be slightly different. The vectorizer will still be the same. That would create this particular column that the decision tree regressor is expecting, and the next stage would be the decision tree itself, and that's what we do here. So that looks good. So we can similar to what we did for the linear regressor, we could build or tune the parameter for the decision tree. In this case, the parameter chosen to tune is the max depth of the tree. And the values in this case were given to you, 2 and 3, but let's say that you could actually maybe put some more, let's say 4 and 5. And then we will build that parameter grid. In this case, we're just doing a one-dimensional version of that grid. And the next thing is using the cross-validator that we have defined here, or we have set the parameters for here. We pass that parameter grid, and then we will fit the model, or we will fit that cross-validator to our data frame, and then from that model, we would choose the best model. So let's run this. This might take some time. And 50, 60, 61 drops. All right. So for this particular one, we also do the same sort of evaluation. So we have the best model from that tree. We transform our test data set, and then the resulting data frame. From the resulting data frame, we select some of the columns. We evaluate that using the regression evaluator, which we had defined previously, and we do it for both metrics, for the RMSE and for the R2. So let's see what happens here. Oh, no. Okay. So you see that in this case, the R2 for this particular decision tree is better. But I think the parameters that were suggested was only to set the depth of the decision tree to be 2 and 3. But I added 2 more, 4 and 5. It just happens that those are actually better for the R2. Well, not so much for the RMSE, but at least it's given a little bit better of R squared. So in that, this is one particular example where, we had set the parameter search space somewhat restricted. Had we, say, looked at other possible values, we would have gotten a better model, but that's the sort of thing that you have to be careful, right? And why you have to be careful is because you cannot sort of go back and forth selecting the parameter and then testing, selecting the parameter and then testing, because then you would go back to the overfitting stage, which means that your model will be very good with data that was used to being built. So in this case, that particular test data set, we are using that to evaluate how good that model is. and that's what we're looking at, the R2 in there. And if we use that particular data, we can run into trouble, right? Because we can get the best possible metric for that particular test set, but then we will not know, we won't know what would happen if we add new data. So one possibility there is to actually have a third data set that you never touch until the very end, and then you can use the test set to, if you wanted to improve the parameter search, and then use a third data set to your final evaluation. But then once you do that evaluation, you can sort of go back and start doing some data snooping, in the sense that you are just optimizing for that one particular data set, but then likely is that model would not will not generalize well. All right. The next thing we can do is that actually, just given that the decision tree is the sort of model is doing selective cuts, so one after the other. So in this case, looks like it's so remember that the one that we got had a little bit more depth. So that's what's happening here. So it's a bunch of else ifs, right? So you will have so if we have so this is the sort of decision that we are going through, or the visual version of the decision tree, where you would split the data and you would select a particular value to create that cut, and then from that cut you would split the data further until you reach all the elements are of one class, or you have reached your minimum, leaf size, which is another parameter of the tree. So here you can explicitly see that tree as well. So somewhat people give to decision trees the benefit that you can explain what the tree is doing. This is in comparison to obviously more complex machine learning algorithms, like say neural networks or even random forests, I would say.
One thing that it's important to note from this example, and you can see it from here in this random forest that you got, is that the result is static or discrete. This is not a continuous model.
Right.
So you see that if you're getting those two features, so if you look at the top right now, you will always predict the number 465.446057, so forth. Okay, yeah. So this is a discrete result, not a continuous result. And, something that people should be aware of, that if you are expecting a result, something that is a continuous value, that wouldn't be something that you would actually want to use.
Yeah, that is actually very useful, because exactly the tree is somewhat passing the event from one branch to the other, and then at the end, how you would decide the value would be the average value for the for those elements that ended up there from the training. So that's how it becomes discrete. So maybe let's do a scatter plot. That would be a good idea. Scatter plot of this metric. Where is it? This one. So we do display that, and then we do scatter, and let's say we're only interested in the predicted for now. Fine. Right, exactly. So this is exactly what AL was saying, that you see the predicted is discrete, as or different from the linear regressor which would be continuous. All right. So one way of improving this model is using an ensemble of trees.
Amanda, can I have a question?
Yes.
Yes. That means your prediction that the values come from the training set, right?
Yes.
Since it's great.
Yes, that's what it means. Yeah.
Okay, I see. Yeah, thanks.
So one way of improving that would be to use an ensemble of trees. So what you would do is you would randomly split your data set, and then you would train a tree from that subset of your data set, and then you repeat that multiple times, and that is the random part of the random forest, and then you would combine all those trees into one ensemble of trees. Let me see. Let's see if I have an image here. Yes. So that is what that particular would look like. So you would have, in this case, 3 trees, and then you would combine the result of each one of them. Okay. And so from the point of view of how do you set it up in Spark, very similar to what we did before for both the linear regression and the tree itself. You would define the regressor, and you would set the parameters for that regressor. So in this constructor, that's what we're doing. We're passing the parameter number of trees equals to 30, the maximum depth of the trees being equal to 8, so how many levels you have in that tree. And then this is the random seed, and that is so we can all compare our results. So if you were to enter a different random seed, you might get different results. And then similar, we can set the label column, the prediction column, the features column, and then, so notice this is one way of setting the max depth of the tree, and this is another way. So these two are equivalent to each other, this one and this one here. The next thing then will be to build a pipeline. You guys are already familiar with that, where the first stage of the pipeline would be the vectorizer, and the second would be the random forest. So somewhat very similar to what we saw previously. Next, let's tune the parameters for this particular random forest. So we're going to build a grid, and in this case, we are building a grid on the maximum bins used for the random forest. You could, in principle, so one of the typical parameters that is tuned is the number of trees of the random forest, the depth, the leaf size. That is another parameter that people typically tune. In this example, we're just using one, but you could add multiple grids. You don't have to. In this case, we're only adding one, but you could add multiple grids. So just for fun, let's do this, and then let's do something like 250. And so that's going to take some time. But I mean, it's very same idea, right? We define for the cross validator, we define an estimator, which is our pipeline, and an evaluator, which is our regression evaluator. So it is the same that we had before. The number of faults is equal to the same, is equal to 3. When you have more data, you could increase the number of folds. So 5 folds, that is not unheard of. That is actually a very common value. But again, it would depend on the data that you might have. And then once the cross-validator is completed, we select the best model once we apply our data set, our data frame. So I think we're getting close to the end. So let me just send you guys the form for attendance so you can start filling that out. So this one is using the UUID, which is this unique identifier. The reason for that, the reason why we went with that is that we noticed that people were using many different email addresses, and because we're keeping track of the points in different places, this would be a way to sort of unify it, because you might have registered with one, but then because we're using the Google groups for the discussions, you would require a Gmail or Google account. So this is our way to unify that. So if that caused any confusion, we apologize, but we figured this is the way to avoid having confusions. So feel free to fill in that form. I will also put it on the Slack in case somebody is following from there. All right. So we build the model. We are tuning it. So we're tuning the parameters of the random forest, and then the next thing would be to, of course, evaluate it. So if we evaluate it, it's actually, I'm just going to copy this for reference. Oops. Sorry. Okay. Oh, wait a minute. So it's not accepting the UID, sorry. Okay, I use the same regex that I use for, so let me correct that. Oh, I see why, because there is no pattern. Okay. Okay, so I'm gonna resend it. Okay, please try again. On that new link. Delete message. All right, thank you. So at this point, very similar, we transform our data set, get the predictions, and evaluate the performance. And let's see if that is any better. So yes, that is good. The mean square error went down, which is good. The R square went up, which is good, it's closer to 1. And if we compare, which is actually the same. Yeah, the RMSE went slightly down, so not a big difference, just by adding those extra parameter points. So that looks good. And again, you could print the value of that RMSE. Just for fun, let's look at that data frame at cell below. and then see what the prediction is. So because we're doing a combination of several trees, that prediction would be slide 1B. So plot options. Let's remove this. All right. So yeah, we don't see the same sort of behavior that we saw. Although, you know, it still could be discretized if you have a small number of trees, but somewhat now the distribution looks much better. So that's it for this session. If people have questions, please make sure you ask them now, or even in the Google groups. Otherwise,